Alright, we're back for linear algebra. Turn that damn thing off. What do we got for Anki? No flashcards. Alright, what did we learn yesterday? Zeros. Zero. What was after? What were we doing yesterday? Identity matrix. Okay, here we go. Inverse matrices. Okay, inverse matrices. So in typical algebra, you got the inverse, the multiplicative inverse. That is, you got the symbol, whatever it is, the value to the power of -1. That's the inverse. It's a multiplicative inverse. And say a is the value. So a times the inverse of a, that's going to equal 1, right? Those are it's also the reciprocal. 1 over a is the same as a to the -1. That's typical algebra. Not the exact same for matrix arithmetic, but let's find the analogous, what would you call it? Not function, but relationship. So if we have a matrix A that is an inverse of matrix A, and that is defined by if A times B equals B times A, and both of those equal I, and the I is the identity matrix. So we're talking about identity matrices are square matrices. So we're talking about for A and B, they've got to be both square matrices in this. They've got to be both square matrices of the same size, and A times B equals B times A equals I. Okay, that's the inverse. All right, but note that does not mean 1 over matrix A or 1 over matrix B. That is not a thing you can do in matrix arithmetic. Division is not a defined operation. Okay, so if we can say, when we got the inverse relationship, we could say that A is non-singular, and we could say B is non-singular, and we could say A is the inverse of B, and we can say B is the inverse of A. There may be another term I'm forgetting, but we'll keep moving forward right now. Okay. Inverse. Singular. So a singular matrix does not have an identity. A singular matrix does not have an inverse. Okay. I'm missing something, but I'm about to get it. It's right in there. What do we got? It's got to do with the inverses. Okay, 1 over A, that's not a defined operation. Singular, yes. If a matrix is non-singular and it has an inverse, it only has exactly one inverse. We kind of proved that statement using the associative property of multiplication. Matrix multiplication, we kind of proved it, so I'm not going to go through it too much, but it only has one inverse if it has an inverse. All right, what do we get into after inverse of matrices? I don't remember. Did we only get through 2 pages yesterday? Oh, we did. Properties of inverses is what we started the next section. Invertible. That is, A is invertible if it has an inverse. B is invertible if it has an inverse. If a matrix has a row of all zeros or a column of all zeros, it's going to be singular, not invertible. Yeah, okay. All right. So we're into properties of matrices right now. Okay. We're about to define the determinant of a 2 by 2, so that's a big deal. All right, I'll be back in a bit to recall what I learned. All right, guys, what did we learn today? All right, for a 2x2 matrix, we can determine if it's invertible by basically determining finding the determinant, which is the values of the main diagonal times together, multiply together, minus the entries not in the main diagonal, multiply together. If that's not equal to 0, then the 2x2 matrix is invertible, and the inverse can be found by 1 over the determinant times essentially if the matrix, you reorder the matrix from A, B, C, D to D, negative B, negative C, A. Okay. All right. Properties of inverses. What else did we do? I don't even know, man. I don't even know. What else did we learn today? Okay. I'm remembering that if A is invertible and n is a non-negative integer, then a to the negative 1 is invertible. A to the all right, I'm pulling it back some of it now. A to the n is invertible, and the inverse is going to be a to the negative n. So a to the n is invertible. A to the negative n is the inverse, vice versa. And k as a scalar times a is invertible, and the inverse is going to be k to the negative 1 times a to the negative 1. What else? All right, we were in a section that comes from a section called powers of a matrix. So we're learning about like powers, exponents. So if a matrix is a square matrix, then its non-negative integer powers can be defined as essentially, if it's a to the n, then it's just a times a times a n times. For negative integer exponents, it's going to essentially be, is it the same thing? A to the negative n is going to be, I don't know if it would be this. No, it would be a to the negative 1, and then all of that times n. And the two exponent rules of exponents, where if you got a base to an exponent times the same base to the exponent, you can add, it's going to be the base to the first exponent plus the second exponent. It's the same for matrices, as well as if you've got a base to an exponent in parentheses times another exponent, that's the same as the base to the exponent times the other exponent. It's the same for matrices as well. Okay, we've got all that. We've got all that. We've got that. All right, with that. The product of two or more matrices that are invertible, if you're multiplying if you multiply two or more matrices that are invertible, the product is invertible, and it's found by taking the product of the inverses in reverse, essentially. Or reverse, yeah, reverse. All right, that's it for today. Talk to you tomorrow. See ya.